Good morning, good afternoon, or good evening, everyone, wherever you might be. So today we're going to be, oh, okay, the recording's starting. Yeah, because the last time I actually did a recording in here and it didn't record. So yeah, I'm just gonna go through what I've written so far about equations of planes. So last time we talked about equations of lines. I did try to talk about planes, but it wasn't recording. But anyways, so yeah, last time we talked about equations of lines, and now we're going to talk about equations of planes in 3D. So apparently, you can use an equation to find a plane or to identify or to draw a plane in some space. Okay, so here's how we're going to do it. So I'm going to read this and I'm going to explain it while I'm reading it, or I'm going to give visuals. Okay, so a plane in space is determined by point P naught, X naught, Y naught, Z naught. So we need an initial point in the plane, right? So let's say you have like this 3D thing, X, Y, Z, and you have, let's say, this plane here. So you need some point. So this is some point with X naught, Y naught, Z naught. You need a point that's in the plane. Okay, and we have a vector n that is orthogonal in the plane. Orthogonal also means perpendicular. So I'm going to write perpendicular. So how is that going to look like? Should have brought back the plane. So let's say we have this plane, a vector that's orthogonal. Let's say that's n. Vector n pointing up. It's orthogonal if it's 90 degrees. 90, 90, 90. So we need a perpendicular vector that's in the plane. Next, we let P be an arbitrary point in the plane. So that is some point in the plane. We let R naught and R be position vectors of P naught and P. So this was actually quite similar to what we talked about previously in lines, and I'm going to show the visual. Oh, no, not that one. There we go. We have R naught here, which points to P naught, and then we have R here, which points to P. So it's the same idea, and they're position vectors because their tail represents the origin. Oh no, it is the origin, actually. Okay, so that's what that means. And then, what else did we get here? Oops. The normal vector, oh yeah, so they're position vectors. So I'm right here. R naught and R are position vectors of P naught and P. And therefore, we have a vector R minus R naught. Now let's actually look at the visual to see how this looks like exactly. So R naught is this guy here, and it's pointing. No, I'm kidding. R naught, scrap that. R naught is that, and it points to P naught. And then R was the previous line I drew, which points to P. And so the vector that connects both of them is R minus R naught. Which makes sense, right? This is, okay, if we do vector addition again, which we did in like 2 weeks ago, or I forgot, 1 week ago, if we go from the origin to here, we can do this R naught. We add it to R minus R naught. We add it to this guy here. And what do we get? We get this vector here, R. Mathematically, you can see that. You just subtract R naught, you get a 0. So R equals R. That's how you get the R. So this makes sense. That's just vector addition. And then the normal vector that is perpendicular, that's there. And then we have P and P naught. And then the blue thing is the plane. So that thing's the plane. Okay, what else did it say? I'm just going over it quickly. Oh, okay, so r minus r naught. So this vector here, r minus r naught, is represented by p naught p because it goes from p naught all the way to p. And we put that right arrow thing to say that it's a vector. And that's true because this is p naught. That's p naught. This is p. So it goes there. P naught. Oh, shoot. My bad. So it goes from p to p naught to p. So that's that. And here, the normal vector n is perpendicular to every vector in the plane. So what does that mean? It's perpendicular to this vector. It's perpendicular to this vector. It's even perpendicular to this vector because we can kind of draw it here. And it's even perpendicular to this vector. You can also draw it here. Now, my drawing's not in scale, so don't mind it, but that's the idea. And in particular, n is orthogonal to or perpendicular to r minus r naught. And since that's perpendicular, these two are perpendicular, the blue arrow or the blue vector and the red vector, in the drawing, then that means their dot product is 0, which we talked about in a previous video. If we have two vectors and they're perpendicular to each other, then their dot product is always 0. And we can actually rewrite this. So we say that's equation 5. We can rewrite it as n times r equals n times r naught. How did we do that? Well, we just did this basically. N times r minus n times r naught. So it's that multiplying thing normally. We can do that, to be honest. And that's just 0, right? And then we add the dot product of n times r naught to both sides. So we would get this equation, which is equal to this. So we add n times r naught, or the dot product of n and r naught to both sides. Then we would get that. That's how we rewrite that thing. And what is this? These are called a vector equation of the plane. Yeah, that's it. And so to obtain a scalar equation for the plane, so scalar means you're multiplying a vector by some number, and that number is a scalar. We rewrite our normal vector n, which has components a, b, c. Those are just some random variables, to be honest. We have r and r naught, and then we have this vector equation. So we just substituted it. So this is n, this is r minus r naught, which is the same as this thing right here. We just made it in vector form, I think. Vector form. Yeah. So that's how we were able to get this. And so a scalar equation would be to just multiply each of these numbers to this whole thing. Right? We just get the dot product of both of the vectors. So we get the dot product of these two vectors. So we can actually say, oh, we're multiplying a to x minus x naught. So that's that. So this and this multiply, then add, because we're doing dot product. Same idea. B times this, C times this. And that should be 0. Right? Okay. Yeah, so we defined it here that a scalar equation of a plane through the point x naught, y naught, z naught with normal vector n is this thing here, which is what we did. We just got the dot product. Okay, So yeah, this example is just, it's there. We just plug it in, right? We have our initial point, which is 2, 4, -1. This thing right here, 2, 4, -1. And then once we get our initial point, x naught, y naught, z naught, as well as our normal vector, which is perpendicular, then we can plug those values in and we get those two. That's enclosed in a box, in a blue box. The other one is just simplified. And so yeah, if we plug in some arbitrary point x, y, z, we can get an equation of a plane. This is basically the equation of a plane. Okay, now we find, yeah, I think one of the question was to find intercepts and sketch the plane. So if we want to find intercepts, then let's say the x-intercept, then we just make y, z 0, right? Because if you remember in 2D, and okay, let's say this is y, this is x. This is a y-intercept because it intercepts the y-axis. This is an x-intercept because it intercepts the x-axis. So this is some x value, but 0 y value. And here, this is some 0, this is some y. When I say some 0, this is 0. 0, and then this is some y. Now, how do we get y? Well, look at that. We make our x 0. How do we get x? Well, look at that. We make our y 0. And so similar to that idea, if we make it 3D this time, now we have x-intercept, y-intercept, and z-intercept. So that's the difference. So here, this is some x 0, 0. This is some y 0, y 0. This is some z 0, 0, z. So what do we do if we want to get z? Make x and y 0. Want to get y? Make x and z 0. Want to get x? Make y and z 0. So that's it. I mean, it's all about conditions. And so that's what we did here in this item, and we managed to get the x and y intercepts of the plane, which is 6, 4, and 3. And now we can sketch that. There we go. Just, yeah, we can just look at this because this is better, because this is the textbook. This one's my pirated drawing. So yeah, that's the plane. It's a triangle plane. Okay. Now we also have this equation here, ax plus by plus cz plus d equals 0. Well, actually, this came from our previous example here. That's where it came from. Because we started with this, which actually came from this, right? A is 2, B is 3, C is 4, x naught, y naught, and z naught are 2, 4, and -1. And then apparently it turned into this. So this is ax, right? Because this is an x. A is 2 plus by plus cz equals 12. So 12 is just some constant, so let's just name it d. And we can rewrite this as this. Plus minus d doesn't matter. So I mean, it's just some constant. So from there we go. That's where we got it. Right? And they actually give a formula for what d is. So there's that. This is how you get d. Just plug in what's known, a, b, c, x naught, y naught, z naught. Yeah. Okay, now here we find an equation of the plane that passes through these points, P, Q, and R. So what can we do first? We can say this is our initial point. So that's P naught, X naught, Y naught, Z naught, right? But the idea is we want to find a normal vector that's orthogonal to the plane. And so what did we do? Well, we got PQ and PR, those two vectors. And how did we do that? Well, P to Q, what's the distance of each of their components? So 3 minus 3 minus 1 is, boom, boom, it's 2, right? 3 minus 1 is 2. And then we do the same thing for our Y and Z components. We get negative 1 minus 3. I'm just going to write negative 1 minus 3, negative 4. 6 minus 2, 4. Basically, what's the change of each component to get from P to Q? And same idea. What's the change of each component to get from P to R? So you do that same subtraction thingy. And then how do we get the perpendicular vector? I mean, we only have two vectors here. So if we want to visualize this, let's say this is P, this is P, I go to Q, here's another one, I go to R. Now, what's the perpendicular or the normal vector? Then that's going to be this thing right here, goes up. And let's say this is vector N. So that's perpendicular to PQ, and it's also perpendicular to PR. So they're both perpendicular to N. So N times this vector should be 0, and N times PR should also be 0. Their dot product should be 0, right? So how do we get that vector? How do we get N? Well, we do cross product, which we discussed. Because cross product allows us to get the perpendicular vector given two vectors. And so we did the cross product, we got N, and boom, that's our N. That's that N pointing up. Or it could be pointing, it's pointing up because the components are positive, see? Plus 12, plus 20, plus 14. So they're probably pointing up. Next thing, yeah, we're not done. We need the equation. So now we use this formula that we got, right? This formula. And okay, so we have our N, which is ABC, 12, 20, 14. We got that, right? A is 12, A is 12, B is 20, C is 14. So we got that. Now we just need our X0, Y0, Z0, which we also got, so we can just plug it in. There's our X0, Y0, Z0. And there we go, we plug it in. We can simplify, then that's the equation of the plane that passes through P, Q, and R points. Okay, moving on. Oh, my charger. Charger's not working. Okay, imagine this dies while I'm recording this. I won't be able to record it again. Anyway, okay, example 6. Well, find the point at which the line with parametric equations. So when we talked about a line, we were looking at parametric equations, right? So we have x is this, y is this, z is this. And it intersects this plane, 4x all the way to 18. So that's the plane equation. This is the line equations. Line equations. Yeah. So how do we find that point which intersects that line and then that plane? How do we find this green thingy? I'm not saying this is the exact points. I'm just saying that's how we're going to find it. Well, we plug in x, y, and z, values of these, to this plane equation. So x will be 2 plus 3t, y will be negative 4t, 5, z will be 5 plus t. At least that's one way I know how. And so I plugged it in. This is x, this is y, this is z. But I do it in terms of t. And now I have one equation. Yay, now I can solve for t. I got negative 2. Now I can plug in -2 to x, y, and z to get the point, the intersecting point of both that line and plane. And I did that, and boom, I got -4 is my x, y is 8, z is 3. Because I just used their parametric equations. And there, that's the point. -4, 8, and 3. And I stopped there. And I realized I wasn't able to record all of that, but now I think I'm supposed to be recording. So that's where we stopped, right? So I hope that makes a lot of sense because I want it to make sense. Okay. Um, yeah, that's it. Okay, moving on. Let's talk about um, what if our normal vector n is not perpendicular? Because previously it was perpendicular, right? So let's say we have two planes are parallel. So here's where the lecture is going to get long. If their normal vectors are parallel, right? And this makes sense. For instance, what do you mean for instance? Okay, we have an example. That's what it means. So for instance, well, we have two planes. So we have planes with equations of x plus, I'm gonna zoom in my textbook. I cannot see. X plus 2y plus x plus 2y minus 3z is 4. That's one of them. Another one is 2x. Is that 2x? Okay. Plus 4y minus 6z, I'm assuming, is 3. I'm gonna move this. Let me move it. I cannot see. Oops, it's not moving. Nice. Oh, I zoomed it in. Okay, we're gonna do that. Okay. X plus 4y minus 6z is 3. And apparently these planes are parallel to each other. Why is that? Well, it's because their normal vectors are parallel. Because normal vectors are parallel. So I'm just gonna name it. Let's say, let's call this n1. And what's the normal vector of this? Well, it's A, B, C. So that's 1. This has a vector of 1, 2, -3. Okay. And let's call the other plane n2. This one has 2, 4, -6. And they are parallel because if you multiply n1 by 2, then you'll get exactly n2. 2n1 is exactly n2, right? So I'm just going to say their normal vectors are parallel. As simple as that. But if two planes are not parallel, then that means they intersect in a straight line. So if they're not parallel, then they intersect. And the angle between the two planes is defined as the acute angle between their normal vectors. I'm gonna show a picture of that real quick, and I'm gonna explain it while I'm also trying to understand what that English means because I'm not an English speaker. I'm kidding. I'm not native. Okay, so let's look at that real quick. Oh, wow, it went all the way there. Did not mean to do that. So that's what this is this figure is. Yeah, it looks like a cardboard with like two arrows. That's anyway. Um, so what this is saying is if two planes are not parallel, I'm just writing it. Yeah. Um, they intersect in a straight line. So it doesn't mean they're perpendicular. I don't think so. It just means they intersect in a line that's straight. Doesn't have to be perpendicular. So apparently this plane, plane one and plane two are not parallel, so they intersect in a straight line. So I think this is that straight line they're talking about. And they intersect here. Actually, that's one. Oh no. No, I think it means this one. Actually, I'm not sure. I'm gonna have to look at it again. They intersect in a straight line and the angle between the two planes. So the angle between the two planes is defined as the acute angle between their normal vectors. See, now what's interesting, see, I find this interesting, but if you look at this flat plane here, right, it has this normal vector, that flat plane, and it's perpendicular. So my intuition was wrong. I thought we were going to talk about what if normal vectors are parallel. Apparently, they're not. We're talking about planes here. So that's the normal vector for that flat plane. N subset 2, or n sub 2, is the normal vector for this slanted plane. And that's why it's perpendicular to this plane. This plane. I did not draw that well. But you get what I mean, right? And then what's interesting is that the angle between these two vectors, this green, okay, I covered it. This theta is actually the same as this theta right there. So that's interesting. So it's saying the angle between the two planes. So the angle between the two planes is this guy is defined as the acute because it's less than 90 degrees between their normal vectors. And between their normal vectors, these are the normal vectors. So I'm gonna write that out real quick. Um, yeah, so it's saying the angle, uh, whoa, between the two planes is defined. So the angle between the two planes is defined as the acute angle. Between normal vectors. So those two red lines. Between their normal vectors. Okay, so I didn't know that. Apparently that's a secret trick. Um, yeah, I did not know that. Not that smart. Anyway, okay, so in math, it doesn't help if we only learn about something but it also helps us if we apply it with an example. So I'm going to do an example. And that example is find the angle between two planes. So that's the first part. So it says find the angle between, and it actually gave us the equation of two planes here. Between the planes x plus y plus, are those pluses? Plus z is 1. And give another one. X minus 2y plus 3z, which I'm assuming is 1, right? Yeah. So how do we do that? How do we find their angle? Well, we can actually find their normal vectors first, right? I think that's what we can do. And then once we find their normal vectors, we can use that formula that given two vectors that intersect and they form an angle. Yeah, I remember learning about that somewhere. I think it was, yeah, 12.2. It was one of those formulas. Where was it? There's no way it's dot product. Oh, I'm kidding. It is dot product. Yeah, you get the dot product of two vectors and you get their angle there. It's these two things. Okay, so we're gonna use that fact here. Yeah, that seems fun. Okay. So first thing that we want to do, I'm not even gonna try doing the textbook. Let's try doing this our way. So we're gonna find, if it doesn't work, I'm gonna look at the textbook and do it. Is we want to find the normal vectors, and let's just call it n1 and n2. And so how do we do that? Well, easy. We just look at their numerical coefficients. So this is 1, 1, 1. Done. That's n1. What's n2? Again, look at their numerical coefficients. 1, -2, +3. Done. Now, from here, what's the angle? Well, we use that formula. So we want to find angle, right? We get their dot product, right? If we get their dot product, it's the same as the distance. So given two vectors, A and B, let's say theta is the angle, this is equal to the length or magnitude of A, length or magnitude of B, cosine of theta, and then we just isolate theta. So we want to use that fact. So we're going to say we get the, ooh, why is it red? We want to get the dot product of n1 and n2, n as in nice, n1 and n2, which is the length of n1, the length of n2, cosine theta. Now we find theta. So n1 and n2, what's their dot product? Well, I have yet to. So yeah, I'm gonna do the dot product. And so that's gonna be what? 1 times 1 plus 1 times -2 plus 1 times 3. And this is 1 minus 2 plus 3. That's what? 2, right? Hang on. I should be right. Yeah, minus 1 and 3, yeah. Now we can get the magnitude of our n1 vector. This is going to be the distance formula. And then it's just 1 squared plus 1 squared plus 1 squared. So it's just 3 squared actually. I'm kidding. It's just square root of 3. And then we got n2, which is again the distance formula. This is 1, -2, -3. So we just put them all in squared. 3. And we're going to get 1 plus 4 plus 9. That is, I am so bad at arithmetic. 14. Now we can put that in, right? So let's quickly plug in these guys. So we have the dot product, which is 2, the length of n1, which is square root of 3, the length of n2, which is square root of 14, cosine theta. Now we just isolate theta and we get the angle. So we're gonna simplify this out. So I can actually multiply. So 14 times 3, I got square root of 42 cosine theta. I'm gonna solve this in degrees, but we can do radians. It doesn't matter. So this is just theta is arc cosine of this guy, which is approximately 2 divided by square root 42. Yeah, which is around 72 degrees, which is what my textbook got. Yeah. So I'm gonna say this is the answer. Okay, that's done. Yeah, so a little bit of application from previous chapters here. Okay, let's look at the next question. The next question is, we want to find symmetric equations. What about these symmetric equations for the line of intersection L of these two planes? For the line of intersection L of these two planes. So right, we're given two equations here. Plane equations. I'm just gonna call them plane equations. So we have two plane equations here, and we want to find symmetric equations for the line of intersection L. What does that mean? For the line of intersection L. I'm repeating it, but then for the line of intersection L. Intersection L. So let's draw my two planes, right? Let's quickly draw those two planes. One was like what? One was like here. Another one was like that. And then apparently there's a line that intersects those two planes. Let's say that line is here. It's line L. Now we want to find symmetric equations for that line. So how do we do that? Well, I think the first thing we need to find is a point on L, right? So ideally, we're trying to find a line equation for L first. So we're trying to find what equation that is. Well, what equation is this thing? So what equation is that? Okay, what is that? So what do we need for an equation of a line in 3D again? Well, if we look at our previous discussion, then we know that we need some initial point, or that's honestly just some point here. And we also need, I forgot. What else do we need? Okay, I'm looking at previous notes here. Oh, we need some direction vector that has ABC. And then let's just say our parameter is t, but it doesn't really matter in this case. So yeah, we can do that. And we have these couple of formulas we can play around with. Yeah. Now the tricky question is, how do we get the point and that vector? So we also need that vector. Oh, notes are long. We also need that vector, which has some components ABC. So let's just do that, yeah. For instance, we can find the point where the line intersects the xy plane. We can do that. I mean, we just need to find a common point. I mean, it could be like any of these points, honestly. Could be this point, could be this point, could be this point. What if, let's say, we want to find the point that intersects or not really intersects. No, I'm kidding, intersects the xy plane. Well, let's just do that. Could be y, could be x, but I mean, could be xz or yz plane, but let's just do xy plane because it's easier. We're used to doing that. So that's the first step. You wanna find a point on that L, that line L. So let's set z to 0. Since we're setting it, we're saying that the line intersects the xy plane. And so let's set z to 0. Yeah, and then let's do what was our plus 2y minus 3z equals 4. So let's do that plane. X plus 3y. Oh, shoot, I forgot. X plus 2y minus 3z is 4. Minus 3z is 4. This is going to be x plus 2y equals 4. And now same idea here. We're doing, what was the other one? 2x plus 4y minus 6z. Wait, am I doing the right example? Oh, shoot. It's x plus y plus z equals 1. Okay, wrong example. X plus y plus z is 1. This is going to turn into x plus y equals 1. Then the other one, I'm going to make sure I'm on the right example here. X minus 2y plus 3z. X minus 2y plus 3z. That's the other plane equation. That's 1. X minus 2y is 1. Great. Now we have two of those. Now what do we do? We solve for x and y. So we say x is 0, 1, line L intersects xy plane. Now we're getting somewhere. We solve for x and y, right? So we can say this is x is 1 minus y. I can do that. And so this is 1 minus y minus 2y is 1. And so this is 1, or I could say 0 actually. Negative 1 and negative 3y is 0. So y is 0, right? So here y is just 0, and so this is x is 1. So I'm gonna put little check marks there. Oh, the red didn't work. And so we can say point 1, 0, 0 lies on L. That's a point that lies on L. Okay, now after observing that, here, since L lies on both planes, right, it is perpendicular to both of the vectors. The line L is perpendicular to both of normal vectors. How does that look like? I'm going to draw it out because I have no idea. Let's say we have this plane. Our line L is this thing. We have some vector here that's pointing there. Then we have another vector here. And so we're saying that this vector, apparently, I have no idea how that happened, but both vectors are perpendicular. I'm checking at the other visual because oh, wait a minute. I was looking at a different visual. I should stop. I'm just gonna look at, okay, I'm gonna copy paste the actual visual for this thing. Yeah, I think they did it in Python or MATLAB. I don't know how they did this, but it looks nice. It looks like or rainbow papers. Yeah, I love that. Rainbow papers cut together. Okay, so we can see our line L as this one. Yeah, making it more visible, more vibrant. And what do we notice about this one? Well, we can say that they're what am I saying? L lies in both planes, so it is perpendicular to both their normal vectors. So what do I mean by that? Let's say we have a normal vector here, and it's pointing like that. It goes like up, right? So how does that look like in like 2D-ish? We have a line here, that vector is pointing up. What do you call this? It's like going to you. It's like going to you. That's what this blue vector is doing. And this is perpendicular. So that's one. Another one actually is this one. So it's this other plane here. That plane there. And so that's N1 and N2. Doesn't matter which order. I'm kidding, it kind of does. Yeah, so it's perpendicular. I'm just gonna write that out. Since L lies on both planes. Yeah, right. Lies on both planes. It is perpendicular to both normal vectors. And so let's just name that um, vector V, right? So we're saying thus a vector V, just name it V, parallel to L is given by the cross product, right? You can do that. Now, I mean, how does that look like? Well, we have a normal vector say it's okay, let's do the previous one. It says like pointing here, right? And we have another one that's pointing here. And we're saying that this and this is perpendicular. Now, what's the vector exactly gonna look like? Vector V. You know what I mean? I'm thinking. Well, actually, one vector is it's probably just gonna look like this. That's probably V, vector V. That is parallel to this thing here, and it's also parallel to the other vector. That's probably vector V. It's parallel, right? Now, I still have no idea why we're doing that. I'm trying to wrap my head around it. Um, Find symmetric equations. Oh, so we need that vector parallel. We're doing that same procedure for line equations where we get the vector parallel and then plug it into getting the line equation, get the parametric equations, and then get the symmetric equations. Right. So let's do that. Let's do a cross product here. So V is N1, the cross product of N1 and N2. Why did I say both N1? N1 and N2. So let's just do a cross product here. So this is 1, 1, 1. That came from where? 1, 1, 1. There we go. N2 is 1, negative 2, 3. So 1, negative 2, 3. And then we can continue solving this. I'm actually just going to do that for practice. Plus, minus, minus, minus. So let's just do that real quick. So let's take out the i's. Let's take out the i's. So this is going to be 1 times 3, negative 2 plus 2. Now let's take out the j's. This is a neat trick. Take out the j's. So this is 3, 1. Let's take out the k. So this is negative 2, 1. And there we go. 5i minus 2j minus 3k. And we get this perpendicular vector. There we go. That's cross product for you. So yeah, now we have that vector v. And we can now we can write a symmetric equation of L, right? But I'm gonna do that. I'm gonna write parametric equations first. Let's try that. I'm gonna find parametric. So how do I find the parametric equations? Well, we have x is equal to x naught. So x naught is, oh, our initial point. Great. So it's just 1. Our initial point was 1, 0, 0. This thing, 1, 0, 0. So this is 1 plus 5d. Our y is, it's just 0. So minus 2t. Z is minus 3t. There we go. Now I find from here symmetric equations. So this is going to be just isolating t. So we have what? X minus 1 over 5, I believe. Yeah. X minus 1 over 5. And there's already a formula for this, but I just wanted to do it this way, just in case. And then here we have 0, I think it was, yeah, there was a formula. 0 or y over -2. Actually gonna equal that. Then we have z -3. And that's it. So it's kind of a similar step here. Okay, so we note since a linear equation in XYZ represents a plane and two non-parallel lines, two non-parallel planes intersect in a line, it follows that two linear equations can represent a line. Okay, let me just reread that real quick. Since a linear equation in XYZ, so a linear equation in XYZ represents a plane, right? We did prove that. And two non-parallel planes intersect in a line, which we also got. It follows that two linear equations can represent a line. That's true. The points x, y, z that satisfy both a1x, b1y, c1z plus d10, a2. Yeah, but basically two linear equations lie on both planes. What are we saying here? We're saying that this line L, it lies on this plane, plane 1 and plane 2. And that's true, right? They have both lines. They have the same, yeah, they have the same line. That same line is in both two different planes. That's just what it's saying. And so the pair of linear equations represents the line of intersections of the planes if they are not parallel. So for instance, in that example 7 that we did earlier, the line L was given as the line of intersection of between two planes. These symmetric equations, we also got symmetric equations, which is again a pair of linear equations. Okay. Yeah, it's a pair of linear equations. They exhibit L as the line of intersection of the planes. Line of intersection of the planes. Oh, when we write the equations of a line in the symmetric form, we regard the line as the line of intersection of two planes. So that's actually quite fascinating here. If you notice, we can kind of, this line, we can say, oh, that line right there can be determined using these parametric equations. Or it can also be determined by these symmetric equations. And so we can say that line L, that linear equation could be this thing, y minus -2. Or that line could also be this thing. So now we have a system of linear equations, right? That's pretty interesting. Yeah, I don't know that. Yeah. So they are apparently, so that's interesting because a line equation, that line L that we did earlier, can be represented by a pair of line equations, which is crazy because if you think about a line, you think, oh, okay, this only represents one equation because it's a line. But apparently, you can represent them in so many ways, or in this case, in two ways. One in terms of x and y, which is this thing, right? That's one way of doing it. That's line L. I can simplify this. This is -2x minus 1 equals 5y. -2x plus 2 equals 5y. This is a linear equation. I can do that. Or I could even do y negative 2, z negative 3. And this is even easier to kind of simplify. 3y equals 2z. So now I have that same line, but it's in terms of y and z. So I could use these bits of information. Let's say I don't have x, at least I have y and z. I can use that to determine the line. And then I can maybe solve for x. Or vice versa. I don't have z, at least I have something in terms of x and y. Or I could even have x minus 1 over 5 is z over negative 3. Negative 3x minus 1 equals 5z. I have something in terms of x and z, which is that same line. Because in 2D, we only have lines, and they can only be represented using one or two variables, right? Well, it depends. If it's a constant, like a horizontal line like this, that's probably, let's say this is 1, then this is just y equals 1. But in 3D, we can represent them up to 3 things, and then we can divide those. And so we have a pair of line equations that represent that same line equation, which is crazy. Anyway, yeah, I'm gonna stop there because it's gonna get too long. Next time I'm gonna talk about, or not even next time, I think I'll probably do it later, hopefully, but we'll see. Next time I'm gonna talk about something related to distances between a point to a plane. Because now we've talked about equations of planes, and then what if we're given some point, what's the distance of that point to a plane? So previously we just did it a bit of intuition, right? From an XYZ, from a point to XY plane, from a point to XZ plane, from a point to YZ plane. But now we're gonna be a bit more flexible. What if it's a plane that's not those standard planes? What if it's like a plane that has an equation, like, let's say we have, I don't even know. Let's say we have like, so we have this plane, this triangle plane that we had earlier. And let's say we had a point like somewhere here. What's the distance of those two? And so we're going to talk about a more mathematical way of how to get that. So yeah, it's just a bit of a teaser. Hope you guys enjoyed and learned something. And I'll see you all in the next one.